We're now going to show that addition modulo an ideal is well defined. That is, we're going to try to put we're going to start to try to put some ring structure on the set of cosets, right? So let's get that started. So if A1, A2, B1, B2 are in R are such that the corresponding cosets for A1 and A2 are the same, and the corresponding cosets for B1 and B2 are the same, then the cosets for A1 plus B1, sorry, my B got messed up there, B1 is the same as the coset for A2 plus B2, which is to say that addition modulo I is well defined. Okay. All right, proof. Showing equality of cosets is just showing congruence modulo I. So we show that A2 plus B2 minus A1 plus B1 is in I because it means the same thing. So to that end, well, let's write it out. A2 plus B2 minus A1 plus B1 is A2 minus A1, if we multiply our negative in, plus B2 minus B1. But A2 minus A1, that's in I, as A1 plus I is A2 plus I. And B2 minus B1, that's also in I, as B1 plus I is B2 plus I. They are congruent modulo I. That was our hypotheses. We're using our hypotheses now. So this is a sum of two elements of I. So this is also in I, because I is an ideal. It's closed under addition. And that's the theorem. That's the end of the theorem. Let's also look at multiplication. So we're going to write down a very similar theorem. Oh, sorry. Just to be clear here, in these, when we're doing this stuff with ideals, I'm gonna. Well, this doesn't require commutative, but so I won't put this here. But our ideals are two-sided, so it's fine. But implicitly, I always mean commutative everywhere. Uh, the results are still going to be true without commutative because our ideals are two-sided. But I do mean commutative everywhere. So theorem. All right. So let R be a ring. Again, in my mind, I'm thinking it's commutative is not strictly necessary, but I am thinking commutative. And I an ideal of R. If we have elements A1, A2, B1, B2 in I, such that A1 is congruent to A2 modulo I, and B1 is congruent to B2 modulo I, then A1, B1 is congruent to A2, B2 modulo I. So what this is telling us is that multiplication modulo I is well defined. All right, so proof. This one's going to be slightly longer. So since A2 minus A1 and B2 minus B1 are in I, because they're congruent modulo I, it's using this assumption right here, there exists X and Y in I such that A2 minus A1 is X and B2 minus B1 is Y, or equivalently, A2 is A1 plus X and B2 is B1 plus Y. Great. Now we're just going to multiply it. Then A2, B2 is A1 plus X, B1 plus Y by plugging in what we have there. So that's A1 times B1 plus a1 times y plus x times b1 plus x times y. Again, our ideals are two-sided, so they absorb multiplication by a1 on the left and b1 on the right. So let me actually write this a little bit better. Let's say then a1y, xb1, and xy are all in our ideal because x and y are, and I absorbs multiplication by ring elements. And since our ideal is closed under addition, a1y plus xb1 plus xy are, that sum is in I. So this tells us then that the difference, a2b2 minus a1b1, it's equal to this expression here, but that guy is in I. So this difference is also in I. And so what we've seen here is that addition modulo I, modulo an ideal, is well defined. And we've also seen that multiplication modulo an ideal is well defined. And if you think about these proofs for a little bit, you'll notice that in the first proof, what we needed is that I is closed under addition only. And in the second proof, what we needed is that I is closed under multiplication by ring elements. That was one of our conditions, and addition. To show that it's a ring, that when we look at cosets modulo I to finish this off, what we're going to do is we're going to need that last condition, that 0 is in our ideal. So we're really using all of the conditions in I to put a ring structure to do arithmetic modulo I.